Hey everybody, I'm back. So we're going to use transformations to sketch this graph. Now the important thing to remember here, because all we really care about with exponential functions when we're graphing them is where is that point that used to be 0, 1? Where is the horizontal asymptote? Normally it's at y equals 0. I think we could figure it out here. It's going to be shifted up 2. And the last thing we need to know is if it's growth or decay. Now remember, we know that an exponential is growth if the base is bigger than 1, and is decay if the base is between 0 and 1. Okay? Now, the number e, hopefully you remember from the last video, the number e is about 2.7182818. And again, you get that by, I think I made up that last part. But it's 2.7, which is clearly bigger than 1. And so this is growth. Okay, the horizontal asymptote is shifted up 2 from normal. Okay, and 0, 1 has been shifted 1 to the right. So it's actually going to be 1, 1 is the point that I'm going to plot. So let's go to my graph. Okay, I'll actually do this one out. We have our y-axis. We have our x-axis. We have a scale. I'm going to go up by 1s in both directions. Okay, so 1, 1 is the point that I'm plotting. It's 0, 1 has been shifted 1 to the right. It's not 1, 1 anymore, sorry. It's also been shifted up 2, so this is a 3. My bad. Okay, so we have 0, 1 has been shifted 1 to the right to make it 1, 1, but then up 2 to make it 1, 3. So this is the point. We have a horizontal asymptote at y equals 2. And we know that this graph is exponential growth. That's all I'm looking for in terms of graphing these. You should be able to identify them. If you were given 4 choices, you should be able to identify which graph is which. If this had been e to the negative x minus 1 plus 2, the big difference here would be that this negative would make 2.718. It would make it 1 over 2.718, which would make it decay. And so this graph with the negative here would look exactly the same, except I would make it decay instead. So just keep that in mind. If you see that negative in the exponent, it actually is taking the reciprocal of the base, which makes it, if it was growth, if it looks like growth, it's decay, and if it looks like decay, it's growth if you have that negative in the exponent. All right, so here's our model for exponential growth or decay, and this pretty much works for every exponential growth or decay problem. We could actually use this model to determine the number of bacteria in the milk culture that we did in the previous video. It would be a little bit more difficult to do it using this model because that one came out pretty evenly, but we could use this. This is the universal model. And so what we have is a of t, which is sort of what's happening at the time that you're asking about. We have a sub 0, which is our initial amount. We have k, which is it's a rate of growth. Now, just because we're increasing at a certain rate doesn't mean that k is necessarily going to be exactly that rate, and that's how it's going to show up. We have to calculate k in some respects. And then t is the time, and the problem will tell you if that time is in seconds, minutes, hours, days, weeks, years, months, whatever it happens to be. The problem will let you know. So looking at this problem, in the year 2000, the human population of the world was approximately 6 billion, and the annual rate of growth was about 2.1%. Using the model for exponential growth, estimate the population of the world in the year 2030. Okay. So, what I'm going to do is I'm going to let t equals 0 represent the year 2000. So we can set our 0 point wherever we want. So t is in years for this, and I'm going to say that when t equals 0, that's the beginning of the year 2000. Okay. That way there, when I use my exponential model, which is right here, okay, I know that since this is population, I'm going to call it P of t is equal to 6, and I'm not going to write the 9 zeros that follow 6. I'm just going to say that P is in billions, okay? So 6 times e to the 0.021 t. So when I plug in 0 for the year 2000, so this is in billions, when I plug in 0, P of 0 gives me 6e to the 0, which is just 6. So I get my 6 billion by setting t equals 0 to be the year 2000. Okay? But I'm not interested in the year 2000. I'm interested in the year 2030. So what number would I plug in for t to get the year 2030 if the year 2000 is t equals 0? The answer is I would plug in 30. So this is going to be 6e to the 0.0121 times 30. And I'm going to let my calculator take care of the rest here. So I do 6. Now I showed you that e is the second division sign, but there's also an e to some power already set up for you as one of the buttons. So if you hit second, and then 2 buttons above the on button on your calculator is the ln button. If you hit second ln, you get e, and then there's already an exponent box set up for you. I'm going to plug in 0.021 times 30 in that box. I'm going to hit enter. I get 11.266 if I round, and that's again in billions. Now, I did write this a little weird, 11.266 billions of people. I could have just written 11.266 billion people, and that would have made sense as well. Now, this model, if we believe it and we think it's accurate, will actually help us go back in time as well. I can figure out what the population of the world was in 1990 if I believe this model. And so what would I plug in for t for the year 1990 if the year 2000 was 0, t equals 0, I would plug in -10. And so I would do 6e to the 0.021 times -10. Now I'm going to give you a pro tip here on your calculator. You can just hit second enter, and it will bring up the last thing you typed in to your calculator. So I'm just going to go up into that exponent now and change that 30 that I had in the exponent to a -10, and I don't have to type in everything else. And that gives me 4.864. Okay. Now you can look up the population of the world in the year 1990 and see if this is accurate. I'm guessing it probably isn't wildly accurate, but maybe it is. So that is it for exponential functions. Next week we will talk about logarithms and solving some pretty tough exponential and logarithmic equations. All right, I will see you then.